So let's look at a picture here that might help kind of explain this. Okay. You think that for this function right here, we believe that the limit as x approaches a of this function is L. How are we going to justify that? Well, somebody comes along and says, well, okay, you think the limit's L. I want you to be within, I don't know, 0.1 of that limiting value. Guarantee that I can always be within 0.1 of that limiting value. Okay? So somebody comes along and they specify this epsilon value right here. Okay? So they say, I want you to get within a distance of epsilon from what you claim the limiting value is. Okay, so a distance means you could either be above it by this much or below it by this much. That's where that absolute value comes in the definition. Okay. Well, let's see if you and I can come up with our delta strip for this. Okay. Somebody said this is their tolerance. I want you to get within this much of the true answer. If I pick this x value right here, if I pick this x value right here and plug it into the function, am I within epsilon of the true answer? No. Everyone see that? If I take this x value, plug it into the function, am I within epsilon of what we're claiming the limit is? No. Does that bother you? Let's call this, let's give this, this is just some x value here, x, maybe x0. Does that bother you? That x0 isn't within the epsilon strip? I mean, I don't think so. It's not that close to A, right? We didn't get that close to A. But what if we pick this x value right here? If we evaluate this in the function, are we within our error tolerance? Yes. So the question becomes, where do I have to pick x values from to guarantee that I'll be within this error tolerance? Where do I have to pick the x values from? Well, it seems to me that, for instance, if I pick that x value right there, would that work? Yes. What about this one way out here?
No.
No. It seems to me that if I pick x values within this much or within this much on either side of A, that I will guarantee that when I evaluate those x values in the function, I will be within my epsilon strip. I will be within the error tolerance that you want me to be within. Okay. What we will pick, though, as far as delta goes, is we'll pick the smaller of these two. Okay, so let me clean this up just a little bit. So we have this distance right here, and we have this distance right here. But I don't want delta to be this distance, because if I go this distance on the other side of A, then I'm not going to guarantee that I'm within my error strip. So delta is going to be the smaller of these two. So this one right here, the smaller of the two, will be the delta value. Okay? So let's just see that we've satisfied the definition of this. Somebody specified an epsilon to us. Were we able to find a delta? Were we able to find a delta? Yes, we were. This is the length of our delta. Whatever that distance is, that's the length of our delta. So that as long as we pick x values within our delta strip, so I look at this as kind of like I call this the delta strip. As long as we pick x values from within that delta strip, we guarantee that our range values will be within our epsilon strip. And that's what we see. As long as I pick x values from within, so this is the delta, this one, so the other side of delta would be over here. So as long as I pick x values within here, I am guaranteed to get y values that are in this epsilon strip. Now, have we satisfied the definition? We didn't satisfy the most important word in the definition. What's the most important word? For every. We were just given one epsilon. What did we do? We found a delta that would make it happen, right? So what if somebody says, hey, the last person specified an error of 0.1. I'm dealing on a much smaller scale than that. 0.1 is not close enough. I want you to be within 0.0002. Well, okay, I still think this is the limit. So I'm going to still add 0.002 above and below it, and that's going to give me a little epsilon strip. Can I still find a delta strip? Yes, I think so. I think, though, in this case, though, my delta strip, there it is, so it'll be on either side, like that. My delta strip is now smaller than it was before. Do you see that? But were we still able to find one? Yes, and what am I claiming? As long as I pick x values from within this delta strip, I'm guaranteed that the y values will be within this epsilon strip. And we keep going. Somebody gives us an even more strict epsilon value. Even still, we can still find a delta. That would be our delta right here. Can we play this game as much as we want? Then what we claim is the limit truly is the limit, because we could do this for every epsilon. Okay. So let's just see where this breaks down. Okay. So again, the same question. Let's suppose you think the limit as x approaches a of f of x here is L. Let's suppose you think that the limit, as we get closer and closer to A, our y values get closer and closer to L. Well, somebody says, okay, I'll give you a tolerance of 0.1. If I give you a tolerance of 0.1, are you guaranteed to be able to find a delta strip here? Yeah, I think so. I think that if you make this your delta strip, and you go either side of it, that when you pick an x value from within your delta strip, you're guaranteed to get y values that are within your epsilon strip. So for this particular epsilon, were we able to find a delta? Yes. How about for this particular epsilon? Would we be able to find a delta? I think so. Okay. Again, let me explain what I'm doing when I'm finding the delta strip. I'm going to go ahead and draw down below here. Okay. And I'm going to take, drawing's not very good. Anyway, I guess this line's not very straight. Okay. So you pick an x value within here, you're guaranteed to be within your epsilon strip. Okay. And then I just take, so sometimes these will be the same size, sometimes one will be smaller than the other. You take the smaller of the two to be your delta. Okay. What about for this epsilon? This is the crux of this explanation. I don't think everyone gives a visual demonstration like this. I think this is for this reason that makes it useful. Okay? So somebody says, I want you to be within this much of what you claim the limit is. There's your epsilon strip. Can you find a delta strip that guarantees any value from the delta strip ends up within that epsilon strip? No, you cannot. We can't find a delta. Or better yet, not that we can't find it, no delta exists, right? Let me say that, no delta exists. So, the limit as x approaches a of f of x does not equal L. We thought it did. The first two epsilons that we picked that worked, we were able to get within that, we were able to get that close, right? Remember? We said early on when we used the phrase closer and closer that that's ambiguous. We don't really know what closer and closer means. Is 0.1 close? Who knows, right? But here we've actually defined that, saying, hey, if you think that 0.1 is close, yeah, you could get within it. But if you think that 0.0001 is close, you can't get within there. So that's not the limit. Okay? All right, so this is a big conceptual demonstration for what we're about to do now mathematically. This is what's happening behind the scenes as we work with these absolute values. Okay? The majority of your homework questions from this will be with these pictures, which I think are really helpful. Okay? Unfortunately, my math lab cannot tell whether you've done a formal proof correctly or not. Okay? So what I'm highlighting as the most important aspect of this section and what my math lab asks you questions on are not in alignment. They're not always in alignment, but here for this section especially, they are completely separate. Okay? So work the my math lab homework. It's good. It builds intuition. But let me just again say that I'm going to ask you to do a question on the next exam, and that question will be one nearly identical to this, up to the numbers. Find that limit.